So this is section 5.5, properties of logarithmic functions. And there's several properties that we're going to be learning today as we go through section 5.5. The first of which involves the fact that if we roll this logarithm into an exponential form, understand that what they're telling us here is that log base pi of pi to the third has a value of 3. All I'm going to do is prove that this is true. So by taking the base of pi, raising it to the exponent of 3, and saying that equals the number right here, which is pi to the third. Well, we know that pi to the third does always equal pi to the third. So where does this come from? And it comes from these two properties right here. The idea is that if the base of the exponent matches the base of the log, then the number in the problem is equal to the simplified value. So in other words, even if they did not tell me that this was equal to the square root of 3, okay, when you look at this problem, because the base of the exponent matches the base of the log, the answer to this problem, the simplified answer, is the square root of 3. Now we're going to learn a property that tells us why that works later, but right now understand that this is just stating that this simplifies to root 3. And this problem right here, remember that natural log, sorry my pen keeps wanting to roll, natural log really has a base of e. So the base matches the number, the base of the exponent matches the number, that comes from this one. If the base of the exponent matches the base of the number, then the final answer, the simplified answer, would be 0.35t. Now there was a typo on your paper. You're going to notice that extra 0, that's not really there. But the simplified version of this is 0.35t. So let's just do a couple of examples of that real quick. Let's say that I give you log base 7 of 7 to the 5th power, and I asked you to simplify that. The base of the log is 7. The base of the number is also 7. So what that's telling me is that this exponent right here is the simplified answer to that problem. So once again, natural log of e to the 5th, since the base of the log matches the base of the number, then that number right there is the answer to the problem. And it works the other way as well. In other words, if I had 5 to the log base 5 of 6, the 5 matches this 5 right here, and so the answer, the simplified answer, would simply be the 6. Once again, I'm going to show you later the reason that works, but just know that's a really cool property to have, that if the base of the log matches the base of the number, or if the base of the exponent matches the base of the log, then you are looking at a simple, very simple answer to find, a very easy way to simplify your problem. The other properties of logarithms that we're going to deal with today are the product law, the quotient law, and then the power law, okay? So the product, the quotient, and the power. If you look right here in this original log, it's log base a of m times n. That's where the product comes from. Quotient, log base a of m divided by n, and power, log base a of m raised to the r power. What they're telling me is that if I start with a single log, that is a product, we can split it into the sum of 2 separate logs. Notice how they started with a single log base a, and we split it into log base a of m plus log base a of n, 2 separate logs. And if we have a quotient in our argument, our log base a of m divided by n, that we can rewrite it as 2 logs that are subtracted, difference, meaning the subtraction. This one is actually one of the most useful properties that you're going to have. And it says that if you have a single log, base a of m to the r power, that you can throw that to the front and multiply it by a single log. So we had started with a single log, ended with a single log. But look where that r ended up? It multiplied in the front of the problem. And we wrote it as a product instead of an exponent. Now, let's look at this problem right here. It says take this problem and expand it. They have told me that the domain is x is greater than 1 because we know, remember that this argument has to be positive. It's always positive for x squared, but it's only positive if this cube root has a value that is greater than 0. And so by setting x minus 1 is greater than 0, we know x must be greater than 1. So that's where the domain came from. But they want us to write a sum of logs. They want us to take this problem, which is x squared times the cube root of x minus 1, and they want us to write it as two logarithms that are added together. Both of those original logarithms will have a base of 2. So we're going to write it as log base 2 of something plus log base 2 of something else. And what that something is x squared and the cube root of x minus 1. Now this is actually written as a sum of logs. We could stop there, except they told us they want us to write all of our powers as factors. That means they want us to throw this exponent to the front. Well, this one's easy to see. We're going to throw that one to the front, and that's going to give us 2 times log base 2 of x. This one's not as easy to see, because what you may not recognize is that a cube root is an exponent also, but it's an exponent of 1/3. Remember, cube root can be rewritten as an exponent of 1/3. So now we're going to throw 1/3 to the front of the problem and write it as log base 2 of just x minus 1. Isn't that a lot easier to see that the argument actually, x has to be greater than 0 for this part, x has to be greater than 1, and we use the most restrictive, and so x is greater than 1 is actually our domain. This is now written as factors because you multiply factors, 2 times log base 2 of x plus 1/3 times log base 2 of x minus 1. Well, let's do a practice problem with the division property. Okay, let's take a division property and take a look at it. This particular problem is divided, and so they want us to write that as a difference of logarithms. We've got log base 6, and we're going to write 2 of them. We took one single log, and we're going to split it into 2 separate problems. So it's going to be log base 6 of some argument minus log base 6 of something else. The numerator is x to the 4th, so that's our first argument. The denominator is x squared plus 3 all squared. So there's our second argument. That would be done. It is written as a difference of logarithms, but it also said, let's express our powers as factors. Once again, they're telling me to throw the exponent to the front. So I'm going to write that as 4 times log base 6 of x minus, and we're going to throw this one to the front, 2 times log base 6 of x squared plus 3. Now, I know some of you are asking right now, well, why don't I split this one as well? Well, you can't split a sum. You can split a product or a quotient, but you cannot split a sum. So this is as expanded as we can make that problem. Once again, let's look at our domain. It says that x can't equal 0. So when we look at this, we know x is greater than 0. Well, in this case, we have x squared plus 3 is always greater than 0, except when x equals 0 right here. And so it's saying any number is allowed. Any number is fine because this is always going to be positive, but 0 is going to be a problem for us. Not a problem here, but it's going to be a problem here. So that's our restriction, and therefore our domain is x cannot equal 0. One more expanded problem. Let's take a look at this. It says write the natural log of a division here with our domain where x is greater than 2. Can you see where that comes from? Right here under this square root, it has to be positive. But then it says write it as a sum and difference. Well, why do you think that there's a sum and difference? That's because this problem is x cubed times the square root of x minus 2 divided by x plus 1 all squared. So this is a product and a quotient in the same problem. So we're going to actually end up with 3 logs. We're going to have the natural log of the first term plus the natural log of this term minus the natural log of this term. So let's write that out. Natural log of x cubed plus the natural log of the square root of x minus 2 minus the natural log of x plus 1 all squared. Now, once again, we'd be finished, except they told us they want us to write our powers as factors. So we're going to throw this 3 to the front, and that's going to be 3 natural log of x. What are we going to throw to the front here? Remember, we can rewrite that as x minus 2 to the 1/2. And so we're going to throw the 1/2 to the front. So 1/2 natural log of x minus 2 minus, let's throw this 2 to the front, 2 natural log of x plus 1. And that is as expanded as that particular function can get. Well, as opposed to expanding, we can also consolidate. We have got 2 logarithms here, we've got 2 logarithms here, and we've got 1, 2, 3 logarithms there, and they want us to express these as a single algorithm. Well, working backwards, remember the last thing we did was expressing our powers as factors. So the first thing we're going to do here is see if there's any factors that we need to throw back up as a power. And there is one right there. We're going to throw that back up as an exponent, and that's going to become natural log of 2 to the 3rd power. See how that 3 went back up as an exponent now. Plus the natural log of x squared. Now that one was already thrown to the top, so we didn't have to throw it again. Now this would be finished, except let's take a look at this. What is 2 to the 3rd power? 2 to the 3rd power is 8, so it's really better to write natural log of 8 plus the natural log of x squared. Now we have 2 logarithms. They are sum. They want me to make it a single logarithm. So in order to make it a single logarithm, since this is plus, we're going to multiply our 2 arguments together. And that's going to give me the natural log of 8x squared, a single logarithm, much easier to look at than this expanded out form. Let's throw this 1/2 to the top. And so that's going to be log base a of 4 to the 1/2. Let's throw this 2 to the top, minus log base a of 5 squared. Okay, so I have to do a little bit of work here. What is 4 to the 1/2 power? That's really saying the square root of 4. So I'm going to rewrite that as the log base a, and the square root of 4 is 2, minus log base a of 5 squared. And 5 squared is 25. So I'm going to write log base a of 25. I've got 2 more simplified logarithms now, but it's subtract. So I'm going to do what to the arguments? I'm going to take these 2 arguments right here, and I'm going to divide them, writing 1 single log base a. We don't write it twice. We write 1 single log of 2 divided by 25. Now this last one is a little bit more complex because there's so many more steps, but let's take a look at this. We've got throwing this to the front, that's going to make that to the exponent, that's going to make that log base a of 3 to the negative 2 plus log base a, we're going to throw this one up as an exponent, 2 to the 3rd, minus, and there's nothing to throw here, log base a of x squared plus 1. Now what you have to remember is if I have a negative exponent, that's really not 3, it's 1/3 squared. So this is log base a of 1/9, that's 1/3 squared, plus log base a of 2 cubed, which is really 8, minus log base a of x squared plus 1. Now I'm going to multiply 1/9 times 8, and then I'm going to divide by x squared plus 1. So we're going to rewrite this as 1 log, and it's going to be the log base a of 8/9, because 1/9 times 8 is 8/9, over x squared plus 1. Now that's a complex fraction. We don't like that. So remember, I can multiply the top and the bottom by 9, getting rid of that denominator, and that's going to give me log base A of 8 over 9 times x squared plus 1. We wrote that as a simple, single logarithmic expression.